We learned from the Pauli Exclusion Principle that an atomic suborbital can hold a maximum of 2 electrons and they must have opposite spins. The electron configurations are visualized by half arrows representing 1 electron each pointing in the opposite direction with a box around them representing the specific suborbital. So how do the electron configurations differ for different elements? Before we go through examples, let's review. First, we must know that as atomic number increase, each element gains 1 more electron. Orbitals are named using their n value followed by a letter that represents the orbital type S, P, D, or F. Each type of orbital is divided into suborbitals, which are the specific regions where electrons are actually located, and each suborbital can hold a maximum of 2 electrons each. The s orbital has 1 suborbital, the p orbital has 3, the d orbital has 5, and the f orbital has 7. Thus, the s, p, d, and f orbitals can hold a maximum of 2, 6, 10, and 14 electrons respectively. For an in-depth explanation of the distinctions between the atomic orbitals and quantum numbers, please check out the attached video, Atomic Orbitals. Starting first with hydrogen, we have 1 electron, so that goes into the only suborbital of s, and we get the electron configuration of 1s1, which denotes the first energy level, the s suborbital, and how many electrons are in it. Next, with helium, there are 2 electrons, which both go into the 1s. The s must get filled before going to p, and we get 1s2. Lithium has 3 electrons, and this is the first time we move up an energy level since the first is full with 2 electrons. The third electron of lithium goes into the 2s, and we get 1s2, 2s1, since we must keep track of where the other electrons are. Beryllium has 4 electrons, so we get 1s2, 2s2. With boron, we move into the p orbitals, and there are 3 suborbitals in the p orbitals, px, py, and pz, and it gets 1s2, 2s2, 2p1. With carbon's 6 electrons, we must introduce a new rule, Hund's rule, which states that degenerate orbitals, orbitals of the same energy level within a subshell, such as px, py, etc., will fill singly and with the same spin as much as possible before pairing up. Therefore, with the electron configuration of 1s2, 2s2, 2p2 of carbon, the electron fills another p suborbital with the same spin before filling the first. Nitrogen has 7 electrons with 1s2, 2s2, 2p3 electron configuration and places an electron in the last p suborbital. Oxygen 8 electrons, fluorine 9 electrons, and neon 10 electrons fill the last of the p orbitals with the electron configuration of 1s2, 2s2, 2p4, 1s2, 2s2, 2p5, 1s2, 2s2, 2p6 respectively. Sodium Na resets the orbital back to s since the energy level of 2 is maxed out, and we get 1 electron in the 3s to make a 1s2, 2s2, 2p6, 3s1 electron configuration. By the way, if you want to find what element corresponds to an electron configuration, just add up the superscripts, and that is the atomic number. As you get further down the periodic table, these electron configurations get extremely long. Therefore, chemists came up with condensed electron configurations as a shorthand way of writing the electron configuration of an atom by referencing a noble gas that precedes the atom in the periodic table. To do this, you must identify the nearest noble gas element that comes before the element of interest in the periodic table. Start the configuration by placing the symbol of this noble gas in square brackets. Follow the symbol with the electron configuration that represents the electrons added after those of the noble gas. So instead of writing 1s2, 2s2, 2p6, 3s1 for sodium Na, we write Ne3s1. Looking at the periodic table closely, we see what it means by the noble gas that comes before the element of interest. These straightforward condensed configurations continue up until argon, which is Ne3s2, 3p6. Potassium is Ar4s1, but what about the 3d orbitals that come after the 3p orbitals? It's been experimentally shown that potassium's outermost electron is in the 4s orbital, skips the next orbital 3d, because the 4s orbital is lower in energy than 3d orbitals. This means that all elements in the 4th row have 4s in their electron configuration. For example, calcium is Ar4s2, scandium is Ar4s2, 3d1, and zinc is Ar4s2, 3d10. This goes a little bit off the rails with copper because it can either completely fill its 4s orbital or its 3d orbital. It turns out that it's energetically favored to fill the 3d, and copper's atomic configuration is Ar4s1 3d10. Once the d orbitals are filled, the 4p1s start with gallium's Ar3d10 4s2 4p1 and end with krypton's Ar3d10 4s2 4p6. From there, the cycle repeats with the 5s and 6s orbitals. Did you notice that as you move down from the 5th row to the 6th row, the condensed electron configuration goes from 5s1 to 6s1? It's not an accident. The periodic table is set up that way. Furthermore, the table I've constructed tells you what orbital the electron goes into, relatively speaking. The pink is S, blue is P, orange is D, and the green is F. But we haven't talked about F yet. With the 6th row, the 7 orbitals of 4F are introduced, which are at a lower energy level than the 5D orbitals. This introduction of the 7F orbitals is the reason why the periodic table has its characteristic structure. If it kept the same outline from before, it would end up being extremely long, seen here. It's important to remember that the periodic table still reads like the longer version. It's just visually pleasing for the F orbitals to be below the others. Thank you for watching, and I hope these explanations help. If you have any further questions, feel free to ask, and if you found value in the video, please like it, subscribe, and let people know about the channel because it really does help spread the knowledge. Based on what you learned, think about the following question. Describe Hund's rule and explain how it applies to the electron configuration of carbon. How is a condensed electron configuration written, and why is it useful? Write the condensed electron configuration for potassium and explain why the 4s orbital is filled before the 3d orbitals. Hund's rule states that electrons will fill orbitals of the same energy level, degenerate orbitals, singly and with parallel spins as much as possible before pairing up. In the case of carbon, with its electron configuration of 1s2, 2s2, 2p2, Hund rule explains why the 2 electrons in the 2p orbitals occupy separate orbitals, 2px and 2py, with parallel spins, enhancing stability by minimizing electron repulsion. A condensed electron configuration is written by starting with the noble gas that precedes the element in the periodic table enclosed in square brackets, followed by the suborbital configuration of the additional electrons. The shorthand method simplifies notation, especially for elements with many electrons, and highlights the valence electrons that are critical for understanding chemical behavior and bonding. AR4S1. The 4s orbital is filled before the 3d orbitals in potassium due to its lower energy relative to the 3d orbitals when these orbitals first begin to fill.